Algebra and Surds video. This one's all about surds. If we've got to simplify this, it would be handy for our brain if we just inserted a little 1 in front of that. So 3 lots of something plus 1 lot of something, I'm here to tell you, is 4 lots of that something. In this case, 4 root 7. Bit hard to spot unless you insert the 1 there to help. 9 lots of something, in this case root 5, minus 2 lots of root 5 is 7 lots of root 5. Nothing wrong with that one. Makes sense. Here, now these aren't like terms, so we can't sort of add how many of each there are and get away with that. We're allowed to kick in a fancy rule here. 63 can be split up into its factors. And so we can write this as root 7, which is that first bit, plus, and if we can split up root 63 as root 9 times 7, then 9 sevens are 63, that's pretty cool. We're allowed then to list them as separate surds, that's a 7 there. So you could say plus root 9 times root 7. Now the good bit about having one of the factors here as a square rootable number, as a square number, is that that can turn into a normal number. So we can have root 7 plus, and root 9 can be 3, and 3 lots of root 7. Now then we can think of, just like in the previous example, we can imagine a 1 being in front of that, invisibly. That helps our brain think that 1 root 7 plus 3 root 7 is a total of 4 root 7. So we wouldn't have been able to do that unless we recognize that any number can be split up into a product of its factors, in this case 9 and 7. Now it's great if we can split that up into using a square number, because that then can be square rooted. And so our square numbers, let's remind ourselves, are 4, 9, 16, 25, 36, 49, etc. If we can split up any bigger number into a product of factors including one of these square rootable numbers, then we can definitely simplify some of these quite nicely. Alright, 4 root 18. So what I'm going to do is say, okay, 4 root 18. Now root 18 I'm going to say is root 9 times 2. And I'm going to say 2 lots of root 8, and I'm going to say root 4 times 2. I'm then allowed to write them as separate square roots, so 4 times root 9 times root 2, plus 2 lots of root 4 times root 2. Now, when we have a 4 here, whoops, let me just kill that one. I'll scrub that and we'll go from there. When we have, sorry about that, 4 times, we can make root 9 into 3. So that becomes a normal number, and then it can associate with normal numbers. Times root 2. And a similar thing can happen over here. We have 2 out the front there, and root 4 can be another 2 times root 2. So our normal numbers out the front so 4 3's can then be 12 root 2, plus 2 2's are 4 root 2. So our final answer there can be 12 lots of something plus 4 lots of something, 16 root 2, which is a lot simpler than what we started with. So we've taken that opportunity again to split up numbers into a product of their factors, one of those factors being a square rootable number. Okay, root 6 times root 7. We are just here to illustrate that that can be root 42. Not much else we can do with that, but if we're able to split terms up, we should be able to then join them as well under the 1 square root. If they're multiplying separately as surds, they can multiply together under the 1 square root, and that can be helpful in simplifying in other questions as well. Alright, now The front numbers in this question can multiply together, making 20. They still have to stay as normal numbers. And the surds can multiply together. So it can be 20 root 6. That's the way that works. Alright, now a couple of different ways of seeing this question. So we could think of this as when we have something that is squared, we can say 3 root 5 times by itself, can't we? That's what squaring is. And the 3 times the 3 makes 9. And the root 5 times the root 5 makes root 25. Now that can go further, of course, because 25 is a square number. So it can be 9 times 5, which makes you 45 there. So that's writing it out separately as 3 root 5 times itself. That's one way of thinking of the squaring. If you just wrote it out this way, this is a second way of thinking of it. When you square something in the brackets, and that's a normal number there, 3 squared equals 9. Now, when you square a square root, that cancels each other out. That square and that square root kind of cancels each other out, and they're beside each other, those two things. So you can think of that as 9 times 5 now, because the square root has been cancelled out by the squaring, and that makes 45 as well. It's just two different ways of thinking about the same result there. You still get 45 for both. So whichever way you like there. Root 18 over root 3. Separate multiplyings can be written under the one individual surd and multiplying. Same with divides. This can become square root of 18 over 3 under the one square root, and you can have square root of 6 because 3 goes into 18 6 times there. So you're allowed to do it that way. Here we can find normal numbers that can go into the top and bottom, so we could say to ourselves 4 goes into that once and into the bottom 3 times. And then you can think of the square root of 5 dividing into the square root of 10 and going twice. So that can go into there twice, but it still needs that square root above it. So we kind of have square root of 2 with a 3 underneath that fraction. So if we did that separately, we'd have sort of 4 over 12, which would turn into 1/3. And if we had a separate root 10 over root 5, that would turn into root 2, which is kind of on the top. So that's how that ends up being the final answer there. Square root of 2 over 3. We're allowed to expand brackets in the same sort of way. There's an invisible multiply here, so we can do the expanding of brackets in the same sort of way, except we consider they're still surds. So root 6 times root 5 is root 30, and root 6 times root 7 is root 42, and we might just leave it like that. So they're square roots. They're separate square roots that are multiplying can be considered to be multiplying under the same square root. Here, pretty similar to the previous question. We'll just have to be a bit more careful because it's got a front number as well. 5 hasn't got anything to multiply except for maybe a 1 there, so the front number will be 5 there, and we could have root 12, 6 times 2. Then the front number 5 can multiply by a minus 3 there, so we get minus 15, and the 2 can multiply with the 11 but under a surd, under a square root. So we can get that. There is an opportunity to split 12 up. If you can consider the factors of each of these numbers that are under square roots, you can perhaps set them up as separate square roots, one of which is square rootable. So we can call root 12 root 4 times root 3 separate surds. Still have this happening. Okay, now that root 4 can be a 2. And then that allows us to then make that into a normal everyday 10. 5 times 2 is 10. Okay, not all that simple, but at least we've expanded it like they wanted us to there. Next one. Pretty similar. That times that, that times that. Well, there will be a special opportunity here in this first term though. Minus 3 times 4 is minus 12. And you've got root 5 times root 5, which is root 25, and that'll simplify quite nicely. For the second bit, you've got a minus times a minus making a plus, and it's kind of like we could consider a 1 in front of that. So minus 3 times minus 1 is plus 3, and that 5 times the 6 separately can be root 30. Now when this turns into a 5, we get minus 12 times a normal number 5, which we will process in a moment on the next line down. And that allows us to have minus 60 for that front bit, plus 3 root 30. So we just expanded that carefully. We were able to turn root 25 into a normal number, and then it can talk to normal numbers from there. Alright, now these ones I like, you can do FOIL if you like, or you can split this up and write it out carefully. So I will be writing out 2 root 6 times that second bracket, and then plus 4 times that second bracket separately. So it's going to take a bit of working here, but still 2 root 6 outside of root 7 minus 3 root 5, plus 4 outside of root 7 minus 3 root 5. So then if we expand that nicely and that carefully, we should be able to see what's happening then. 2 root 42, 2 times that, the 6 and the 7 can multiply separately. 2 times minus 3 is minus 6 root, now you got 6 times 5, so you'll have root 30 there. Plus 4 lots of root 7, doesn't need much thinking about, and 4 times minus 3 is minus 12 root 5. That's a bit easier, that bit. Now, do we have any like surds? You know, if we had 2 lots of root 5s here, we could join them up into the 1, but nothing is common there, so we're just going to leave it like that, I believe. Let me check. I think we're pretty right there. Yep, looking good. Alright, not much extra simplifying opportunities there. Okay, now, a couple of ways of doing this. If we were to split that term and expand it, we could have something very special happening. And that is that there'll be some middle terms that'll cancel each other out. I mean, you could try that yourself if you like. Expand that out, say root 5 times the second bracket, minus root 2 times the second bracket. But I'm here to tell you there's something special happening here. And the reason I know there's something special is you have a look at the contents of that term, of that bracket, sorry, and the contents of that bracket. The only difference is the plus and the minus in the separate brackets. So this actually fits into that difference of 2 squares type situation. So this actually equals root 5 squared minus root 2 squared, which is fantastic for simplifying this out, because a square and a square root cancel each other out, leaving us with 5. And once again, a square and a square root cancel each other out, leaving us with a 2. 5 minus 2 is 3. That works out a lot simpler than you ever thought it would. So that'll work if you do it the long way around, but we were able to spot there that it fits into that rule that says if you've got a plus b, so any term with a plus in between it, any 2 terms with a plus in between it, and the same 2 terms with a minus in between it, that equals that a squared minus b squared situation. So if you can spot a shortcut like that, it cuts down the workload, that's for sure. Okay, when we square this, we could write it out twice. 4 root 7 minus root 3, and then another bracket of 4 root 7 minus root 3. Or we can spot a shortcut that we can do as well. So, so when we've got a minus b all squared, That equals the first term squared minus 2 lots of these two terms multiplied together plus the second term squared. So let's go with that shortcut. I mean, we could do that as well. There's no problem with doing that, but it takes longer that way. So if we took the first term and squared it, we'll have 4 root 7 squared minus 2 lots of the first term, which is 4 root 7, lots of the second term, which is root 3, plus the second term squared, which is root 3 all squared. So when we process that, we get 4 squared, and the square will cancel out the square root for the 7. So you'll get 16 times 7 for the first bit. Here we have minus 2 times a 4, we get minus 8, and the two square roots can multiply inside a square root that's sort of joining those two up. And the square and the square root will cancel out there, leaving us with just a 3. So 16 times 7 is something big, 112. Okay, so we get 112 minus 8 root 21 plus another 3, and we'll end up with 115 when we add the 3 and the 112 minus 8 root 21. So spotting the perfect square scenario here, if you know all those shortcuts for perfect squares and difference between two squareds, it actually comes up in the Surds chapter as well. Now we're looking at rationalizing. This is to get the denominator, the bottom of a fraction, to be a rational number. At the moment, root 5, square roots of non-square numbers are irrational. The way we do it is to multiply by the bottom over the bottom. So that'll help a lot. 1 times root 5 is root 5. Square root of 5 times square root of 5 will end up being 5. The reason is that square root of 5 times square root of 5 is root 25, and that turns into 5 there. So there's your final answer, root 5 on 5. Rationalizing this now, that the 2 on the bottom is a normal number, so that's not the problem. So we're allowed to just multiply by the bit that's the problem, root 3 over root 3 in this situation. Now that root 6 times the root 3 can join up, 5 root 18 over, now this will be 2 times root 9, 5 root 18 over 2 times 3, 5 root 18 over 6 would be our answer there. Now, I just spotted that there's an opportunity here to go a little bit more simple here. We can say 5 root 9 times root 2. Aha! So we've always got to check whether there's a number under a square root that is actually able to be expressed as factors, one of which is a square number. So that gives us 5 times 3. That root 9 can be a 3 times root 2 over 6 ends up being that we can then cancel out. There's a lot to do here. We can say 3 goes into itself once and into there twice. And so your final answer, if you're careful enough, I almost didn't spot that bit. 5 times 1 times root 2 is equal to root 2 on the top. No, 5 root 2 on the top over 2. 5 root 2 over 2 is your final answer. Rationalizing this, we will want to multiply by something that'll get the bottom to be a rational number, in this case root 11. Okay, now here we have to remember that that's brackets. There are two things on the top there that are getting multiplied by root 11, so it's almost like we're backwards expanding this. A bit weird, but still. 2 root 7 times root 11 is going to be 2 root 77 when we multiply the 7 and the 11, plus 3 root 11 over 11. This will cancel each other out, the square and the square root. That's why we did it that way. So that's a pretty interesting way of doing that. Just be careful on the top there that you multiply that root 11 by both terms individually there to rationalize that bottom. Here, what we have to do is multiply by what they call the conjugate, which is the same numbers as the bottom but with a different sign in between them. So we're going to have to multiply by root 5 plus 7 over root 5 plus 7. I'm sure you remember this from class. Here we'll be a bit careful and expand that separately, so we'll have 3 root 5 plus 3 lots of 7 is 21 over, now this sets up one of those a minus b times a plus b situations, which ends up being a squared, the first term squared, minus the second term squared, which is great for cancelling out square roots. So if we squared that first term, we would get 5, and minus that second term squared, which would be 49. 7 sevens are 49. So we end up with 3 root 5 plus 21 on top, and 5 minus 49 is minus 44. So we're multiplying by what we call a conjugate there on top of itself, so that overall we're multiplying by just 1 on that right hand side, which is fine. Multiplying something by 1 doesn't change it at all, does it? Okay, and that's a whole bunch of surds there. I hope that helps. Quite tricky, but get the hang of all those rules. They're not too bad once you get the hang of them. peterblakemaths.com. Catch you next time.